and the light is still gray when the first hive boxes come off the truck, stacked 8 high, humming with a sound that the orchard's 12 hectares of bare-branched apple and cherry trees had not heard in years. This grove had failed to produce a viable yield for 6 consecutive seasons. Not a slow decline, not a modest shortfall, but 6 years of blossoms opening and closing without setting a single marketable fruit, while the cooperative that owned it watched its losses compound and its options narrow to almost nothing. The silence had started quietly, the way these silences always do. Back in the years when broad-spectrum pesticides were still considered standard orchard management, and the insects that kept everything running were treated as incidental casualties of a system that did not yet know what it was losing. I'm Dr. Raymond Finch, and in 40 years of watching ecosystems respond to what they had been denied, I have never seen a living system move faster toward its own recovery than this orchard did the moment 50,000 bees were given back the role we had taken from them. A commercial beekeeper had arrived at dawn carrying 40 hives, an estimated 50,000 bees in total, and within 90 minutes of the first boxes being opened, every visible blossom across the lower canopy was covered. Not one row, not one section. All of it simultaneously. Dr. Sarah Okafor, a pollination ecologist contracted by the cooperative, was standing at the edge of row 7 that morning with a pollen transfer counter she had calibrated across 3 previous orchard restorations. And she was expecting exactly what those restorations had taught her to expect. Measured, careful, incremental activity in the first few hours. Now, think about what that means for a moment. Her baseline model, built from 3 verified field restorations, predicted a specific visitation rate for morning 1. What her counter recorded before 10 a.m. was 4 times that number, not by the end of the day before breakfast. You are watching a system that has been holding its breath for 6 seasons, and the moment the trigger returned, it did not ease back gradually the way the model said it would. It fired, immediately, completely. The way a compressed spring releases when the last pin is pulled. You are probably asking yourself right now whether this was simply a lucky morning, the right temperature, the right wind, a coincidence of conditions that Okafor's instruments happened to catch. That question is the right one, and the data from the next 3 weeks of field observation answers it in a way that will change how you think about what an orchard actually is. Stay with this. What Okafor had stepped into, without yet knowing it, was not a pollination event. It was a biological system responding to the return of its missing keystone trigger across 12 hectares of trees that had been physiologically ready for years to do exactly this. The capacity had never left, only the bees had. Rows of trees in full bloom, petals white against the April light, canopy after canopy dressed in the precise costume of productivity. A grove that looked, by every visual measure, like it was doing exactly what a grove is supposed to do. But Dr. Sarah Okafor had not come to look at it from the road. The season before the reintroduction, she pulled pollen viability samples from 6 representative rows, a methodical baseline sweep that took 3 days and returned numbers the cooperative had never seen written down in a single report. Fruit said, the rate at which a pollinated flower actually becomes a fruit, had collapsed to 11% across the grove. A healthy commercial grove runs between 55 and 70%. What Okafor had measured was not a bad season. It was a biological system producing at roughly 1/5 of the minimum threshold required to be called functional. This is the part that made me stop and reread the field notes. Because the cooperative had run pesticide audits, they had adjusted irrigation schedules, they had replaced rootstock, and not one of those interventions had touched the actual variable that was failing, the living insect that closes the loop between a flower and a fruit. And the Wenatchee Grove was not an isolated case. In the Central Valley of California, almond groves had documented a 40% yield reduction across more than 400,000 hectares, where wild bee populations had dropped below detectable thresholds. Not reduced, not thinned, but gone past the point where standard surveys could find them. In the Yakima Valley, just 90 miles south, wild pollinator counts in apple orchards fell by more than 70% between 1998 and 2016. And the growers who noticed it first were the ones watching their neighbors' field margins go quiet. In the Hood River Valley of Oregon, cherry yields collapsed in 2017, the same winter that managed honeybee colony losses in the Pacific Northwest exceeded 35%. In the Okanagan Basin, entomologist surveys documented fewer than 8 native wild bee species still active in commercial orchard zones, down from a historical baseline above 30. The blossoms were open. The machinery was present. The biological actor that converts a flower into a fruit had become a ghost. A tree in bloom is not a tree in production. That distinction sounds simple, but it had been invisible to decades of commercial management because blossoms photograph beautifully, and nobody was counting what happened to them afterward. What Okafor's insect surveys found underneath the fruit set data was a collapsed pollinator community. No ground nesting species detectable along the field margins, managed honeybee visitation sporadic at best, and wild solitary bee activity reduced to trace-level counts that her counter registered as statistical noise rather than ecological presence. You are probably asking right now how a grove reaches this point without the people running it understanding what was happening. That is precisely the question Okafor's 2019 field report addresses. And what it found in the soil chemistry and the historical pesticide application records is what makes this particular restoration different from every other case I have documented in 4 decades of fieldwork. The answer is coming. Stay in your seat. The trees had not failed. They had been waiting, holding the physiological capacity for full production in suspension, season after season, while the one trigger that would release it was absent. What the deployment of 50,000 bees was about to reveal was not a recovery. It was a deferred response, 6 seasons deep, finally given permission to arrive. Fails you, and the deadline is still coming. They hired people. They put 6 workers into the highest value cherry rows with soft brushes, moving blossom to blossom by hand across 4 hectares, doing slowly and imperfectly what a living system once did without being asked. Those 6 people worked a full day to cover ground that a single healthy colony of 15,000 bees processes in under 2 hours. And that gap is not a management inefficiency. It is a biological gap that no payroll can close, because the bee is not just a delivery mechanism for pollen. It is calibrated by 80 million years of coevolution with the flower itself. The cooperative spent 3 seasons and an estimated $180,000 on that substitution program. $180,000 that bought them a measurable but inadequate result, and a very expensive lesson in the difference between a solution and a workaround. After 2 full years of that program, fruit set in the hand-pollinated rows climbed from 11 to 19. A real gain, recorded in verified crop data, but still less than a third of the 55 to 70 benchmark that a functioning pollinator community delivers without a single hour of labor. Here is where the data stops being data and becomes something else entirely, because in 2016, the Washington State Department of Agriculture formally recommended that hand pollination protocols remain the primary response to pollinator decline, citing concerns that large managed honeybee colonies placed near chemically active blocks could complicate pesticide scheduling and create liability exposure with neighboring operations. That recommendation held for 3 years. 3 years during which the cooperative kept paying crews, the trees kept underperforming, and an 18-meter perimeter buffer strip around the orchard sat chemically quiet for the first time in over a decade, classified by management as agriculturally unproductive and largely ignored. What happened inside that buffer, once the late spring insecticide applications were suspended, is the detail that the original cost-benefit analysis never modeled. Wild mason bee activity increased within 1 growing cycle, adding a secondary pollination layer that nobody had designed, nobody had paid for, and nobody had anticipated. You are probably asking whether that secondary layer was significant enough to measure. And the answer is in Dr. Sarah Okafor's notebooks from week 6 of the reintroduction. She recorded 3 native species foraging actively in that buffer, species her 2018 baseline survey had logged as entirely absent from the 12-hectare site. They had not gone extinct. They had simply been excluded, and the moment the chemistry relented, they returned. The mechanism behind how quickly that recolonization scaled is what Act 4 is going to show you, and you will want to see it. The cooperative had tried every substitution available to them: manual brush application across 4 hectares, extended crew rotations, and $180,000 budget commitment across 3 attempts. And each one confirmed the same structural limit. Human labor can approximate pollination, but it cannot replicate the density, the timing, precision, or the metabolic consistency that a living colony maintains from first light to last. 90 days. That is how long it took 50,000 bees to rewrite a conclusion that 3 years and $180,000 had calcified into institutional policy. A single forager lands on an open apple blossom. Her thorax brushes the anther, and pollen grains, each one between 30 and 50 microns across, lock into the dense hair covering her body. She moves to the next flower within 8 seconds. The pollen reaches the stigma. The ovary wall receives the signal it has been waiting for. Fertilization begins, and the tissue that will become the fruit starts quietly to swell. That is 1 bee, 1 flower, 8 seconds. Now multiply that by 50,000 animals working 12 hours of daylight across 12 hectares, each individual making between 50 and 100 flower visits per foraging trip, then returning and going out again. The same sequence, compounding hour after hour without interruption. By day 4 at the Wenatchee site, Dr. Sarah Okafor's fruit set counters were recording figures she initially assumed were instrument errors. Fruit set had climbed past 48% across the monitored rows, representing more biologically completed fertilization events in 96 hours than 2 full seasons of brush application had ever produced. 48% fruit set. In a grove that had returned less than a fifth of that figure across 6 consecutive failed seasons, that number did not represent progress. It represented the orchard remembering, at a cellular level, how to do its one essential job. Here is where it gets interesting, because what happened next was not part of any restoration protocol Dr. Okafor had written, and it is the reason every soil ecologist who has reviewed her field report from April 2019 has gone back and re-examined their own assumptions about pollinator-driven recovery cascades. Stay with this, because the answer is closer than you think. By week 3, Dr. Okafor documented the return of 5 ground foraging beetle species to the orchard floor. Insects that feed on fallen pollen and floral debris, that process organic matter into available soil nutrients, and whose last recorded presence on the site predated the cooperative's heavy insecticide rotations of the early 2000s. Their arrival was not engineered. The system simply recognized that biological flow had resumed. The beetle does not know it has been absent for 2 decades. It knows only that the resource chain it depends on, pollen, debris, decaying floral tissue, has reappeared in the orchard floor, and so it has followed that signal home, exactly as it was built to do across millions of foraging generations. By the close of that first season, the 12-hectare grove at Wenatchee produced a commercially viable yield for the first time in 6 consecutive seasons. Not because anyone intervened at the soil level, not because a remediation crew arrived with inputs, but because 50,000 animals did what they have done for 100 million years, and the orchard remembered exactly what to do with that signal. What Dr. Okafor's report confirmed, and what Act 5 is going to take you inside, is that the recovery did not stop at the canopy. The cascade she began tracking at week 3 was still accelerating when the season closed, and what it was moving toward is something the agronomists on that project had no framework to anticipate. Deployment confined within a 12-hectare boundary, colonies removed after peak bloom. A cooperative, a beekeeper, a handshake, and a map with a drawn perimeter. Nobody consulted the bees. By day 10, Dr. Sarah Okafor's pollen tracing data, pulled from fluorescent dye she had applied to 3 marked hives at the Wenatchee site in April 2019, showed foraging activity reaching 2.4 kilometers beyond the eastern perimeter, deep into a hedgerow corridor nobody had mapped as part of the restoration zone. 2.4 kilometers. That is not a small deviation from a management plan. That is a forager covering ground the cooperative had no jurisdiction over, moving through a mixed hedgerow and into an abandoned 3-hectare block that a neighboring landowner had already earmarked for a parking surface for agricultural equipment. The bees had found wild mustard in that uncultivated block, and they were working it in tandem with the managed trees, which meant wild plant pollen was appearing inside apple blossoms, and apple pollen was appearing in the wild mustard. A cross-pollination event spanning a landscape boundary that no management document had anticipated, and no agronomist on the project had a framework to evaluate. Within 4 weeks of the bees passing through that uncultivated block, Dr. Okafor recorded 7 flowering plant species in a space where no prior survey had documented a single one. Opportunistic bloomers that had simply been waiting for a pollinator dense enough to make reproduction viable again. The neighboring landowner was not pleased. You can understand why. This was his land, his plan, his timeline for converting it. What he could not have known, and what nobody on the cooperative had predicted, is that the biological process now running in that 3-hectare block was not finished making decisions. You are probably wondering at this point whether a handful of wildflowers and an unhappy neighbor is really the story here. And I want you to stay with this, because what Dr. Okafor documented in that same block during the 2nd season is the part that made the agronomists on this project go very quiet when they read her report. 14 months after the honeybee reintroduction, 14 months, not a decade, not a managed rewilding program, a colony of native bumblebees established a ground nest in the uncultivated soil of that 3-hectare block. One of 3 species listed as regionally declining. No hive box, no beekeeper, no management contract. Nobody hired them, and nobody could remove them. The 50,000 honeybees had arrived as a temporary measure, a contracted intervention with a removal date written into the agreement. What they left behind, in a block that was 2.4 kilometers from where they were supposed to stay, was a self-sustaining resident pollinator population, a permanent biological presence seeded by 40 hives that no longer live there. What that resident colony did to the surrounding landscape in the seasons that followed is where this story goes next. Wenatchee Valley, the way it always does, cold mornings, pale light across the ridge, blossoms opening row by row, whether anyone is watching or not. The trees did not know they had been written off. They simply did what trees do when the conditions return. They fruited. Dr. Sarah Okafor filed her 2020 field report from that same 12-hectare site she had first walked in, April 2019, and the language she used was the language of a scientist who has trained herself not to reach for words she cannot defend. She wrote that recovery had outpaced every model applied to the site, not met, not approached, outpaced. The orchard delivered its first commercially graded apple and cherry harvest in 6 consecutive seasons, 6 years during which every yield assessment had returned the same verdict. Non-viable. A single returning pollinator community had closed that gap in less than 2 full growing cycles. I have spent 40 years watching systems that people had declared finished find their way back to function the moment the missing piece was returned. And the piece is never complicated. It is almost insultingly simple. The tree knew how to make fruit. It had always known. It was only waiting for the one animal that completes the sentence the blossom begins. Think about what that actually means for the valley as a whole. Not just for one orchard, not just for one season. The pollinator community that established itself in the uncultivated soil 2.4 kilometers from its original assignment did not serve a single crop. It served every flowering plant within its range, which, by the 2nd season, extended across at least 3 distinct land parcels that had never shared a documented pollination event. By 2021, a follow-up survey documented 14 flowering species returning to field margins that had been ecologically dormant for over a decade. Not seeded, not managed, not encouraged by anyone. Physics, moving at the speed of a bee in flight, had done in 2 seasons what no replanting budget had achieved in 10 years of prior attempts. You are probably wondering whether this recovery holds, whether 2 good seasons mean permanent restoration, or whether the system is still fragile enough that a single hard pesticide application on a neighboring parcel could unravel it. That answer exists in Dr. Okafor's longitudinal data, and it is more reassuring than you might expect. But you need to stay with me through what the data actually says about resilience thresholds, because the number that matters is not the one you are picturing. What Dr. Okafor's report ultimately confirmed comes down to 3 documented realities. The trees retained the biological capacity to produce across 6 dormant seasons. The returning pollinator community required no human maintenance to persist, and the landscape recovery extended well beyond the boundaries of any agreement anyone had signed. Recovery is not hope, it is physics, and physics does not ask for your permission before it begins. Drop your region and one species you have personally watched disappear from your area in your lifetime. Name it in the comments, because that absence is data, and data is where restoration begins. And yes or no in the comments, have you ever seen something come back that you were certain was gone for good? Because if the answer is yes, I want to hear that story. Share this with someone who still believes the damage is permanent, because the evidence says otherwise. I'm Dr. Raymond Finch. I'll see you in the field. Next, I am taking you to the chalk streams of southern England, where brown trout have returned to a 14-kilometer stretch of the river test that was declared biologically dead in the 1990s. Fish density surveys recorded a 300% increase in spawning pairs within 5 years of macrophyte restoration. The Environment Agency opposed the removal of water abstraction licenses on that stretch until 2011. And that single policy delay cost the river an estimated additional decade of recovery. The question the test still cannot answer is whether its invertebrate communities can rebuild fast enough to feed the returning trout before the fish outgrow what the stream can currently provide.